Okay. So when you talk about derivative, now you're specifically talking about the exact rate of change function. It has to be the exact rate of change function, not the rate of change function that we've talked about so far, which is flexible. It could be approximate or exact. Derivative is necessarily exact rate of change. So we did an example last week, if you remember, and this was the exact rate of change function for that. We kind of investigated, we zoomed in on points, and we tested it out, but whether you remember that or not. So therefore, negative 12 over x plus 2 squared is the derivative of g. We derive it from g, and it's the rate of change function for g. Okay? So there's different notations for the derivative. You'll see this. dg of x dx, or dg dx. You'll also see that. It's possible. And that's descriptive notation. Why? Because the derivative is what? Change in y over change in x for very, very small changes of x. So this notation is kind of the most representative of the function itself, because you actually see in the notation change in dependent over change in independent. Okay, you also see this, g prime. So remember, in GC, in graphing calculator, prime means open up a new graphing window. Totally separate meaning, right? Totally different meaning. This now is talking about the derivative of g. This is the derivative of g. Okay, so is this the derivative? Is this only if h is small? Again, when we're talking about derivative, you have to have that small h for the exact function. So if we put a limit notation in front of it, now that's saying, this is essentially saying let h be essentially 0, or atomically small, okay? Let h be sufficiently small. It's very, very, very close to 0, and then now that expression gives exact rate of change, and that would represent derivative. As opposed to just this function that we've been working with, we said was versatile, right? So it could be approximate rate of change when h is not small. If h is small, then it is exact rate of change. Okay, but these up here, these are all notations for derivative and exact rate of change only, not approximate rate of change. So the rules, what? So the rules that we're starting to learn now are what we call the derivative rules. Derivative rules, shortcuts, fast tracks to getting an exact rate of change function. In order to derive the rule, though, we always start with the rate of change function, and we do the algebra, and then we can create these rules for being able to crank out these derivatives quickly, algebraically. So that's what we're working on right now is the derivative rule. So we've got 4. Let's keep going. Next rule, rate of change of the square root function. Rate of change of the square root function. Okay? If we want to derive a shortcut rule for a function that's square root of x, where do we start? Where do we begin? Everyone write it down. Where do we begin? And I got my list today. Okay, where's Trista Thacker? Where's Trista? What do we do first if we want to derive or come up with a shortcut rule for this kind of function? Good. And what would that be for this particular function? So f of x plus h is going to be what? Square root of x plus h. And then f of x is square root of x over h. So we start with our rate of change function. And now we're going to do the algebra to come up with a shortcut form for finding the rate of change or the derivative of square root of x. Okay? And so remember that from algebra 2 that a minus b times a plus b is a squared minus b squared. And we're going to use that to get rid of these square roots. So what do I want to multiply the top and bottom by so that I can apply these rules and then the square roots will go away? Do you see? On the top. What will I multiply the top and bottom by? Let's see. Where's Julie Alvarez? Julie, are you here? Do you see what we'll multiply top and bottom by? So in the numerator, we'll get rid of the square roots by applying this rule in red here. Okay, so then it'll be like a minus b times a minus b. So, you almost had it. Right, so if we multiply the top by square root of x plus h plus square root of x, we'll end up with a squared minus b squared, which makes the square roots go away, right? But then we got to multiply that by the bottom as well. Okay, so here's the first step. It's not hard, you guys. It's not hard. Don't freak out. Okay? And so we know the top just becomes what? X plus h minus x. And we're going to leave the bottom just like it is. We don't have to do anything on the bottom. So now I've just applied the rule that's in red there. A minus b times a plus b is a squared minus b squared. So the numerator becomes just h. H over h goes away. And when h is really small, so I kind of went a little faster. All right, so x minus x is 0, so all we have left in the numerator is h. Right? H over h is 1, so our h's go away. And then also we want h to be really, really small. When h is really, really small, then after the h's go away, we're left with this, which is 1 over 2 square root of x. When h is really small. So we've got our derivative for the square root of x is 1 over 2 square root of x. That's our shortcut rule for the derivative of the square root of x. Yes, I know your question. Hold on a sec. I know what it is. Okay, but these people raising their hands, they're noticing that. What is the square root of x? The same as. What function is that? X to the 1/2. Right? X to the 1/2. And we can apply one of our rules that we have already to x to the 1/2. And what is it? So it'll be. Now, this isn't. This is just using the power rule to check our answer. Okay? So this isn't a formal derivation. This is just using the power rule. And so 1/2 x to the minus 1/2. Is it the same as what we got? Yeah, because x to the minus 1/2 is just square root of x in the denominator. X to the minus 1/2 is 1 over x to the 1/2, which is 1 over 2 square root of x. Same thing. So we just confirmed our answer using the power rule. Okay, anybody have a question? All right, so then you did this in the homework, so let's do one together in class here. So our algebra is always prone to mistakes, and how can we check our result graphically with GC? Okay, so both of these we got the same answer, but both of them we did with algebra, right? We had to perform algebra to get this 1 over 2 square root of x. And so how can we check it? Let's do that. So the accumulation or amount function was square root of x. Okay? And by algebra, derivative we got was, so let's just call that, what should we call that? I'll just call it g, okay? Because we're going to save r for the trusted. So what do we get? 1 divided by 2 square root of x. All right, so that was by algebra, so it's not, we're prone to mistakes, but what do we trust? Okay, so we could say, what is the trusted form of the derivative? So that's our r, I call r of x, just for simplicity. What's the trusted form of the derivative of f that we know for sure is right? Where is Kyla Richardson? Is Kyla here? What's our trusted form of the rate of change of f? Good. We know that's right. If we've got our function right, now we know that our x is right, okay? But we want to make sure that it is exact rate of change. So what can we do to make sure it's exact rate of change? Where's Lester? Nangbo. Yeah, what can we do to make sure that that thing is exact rate of change? Okay, and so how can we set an h so that it's like approaching 0? No, we want it. We just want to have an h value. So like, how about like 0? Yeah, like point something really small like that, 0.0001. Okay. We don't want to do 0 because what? Then our Rx function is undefined. We want essentially 0, but we need change. You can't have rate of change without some change. You can't have rate of change without a little bit of change. We just want to make it small enough. Okay, and so now what are we going to do? We're going to graph. Which two are we graphing and comparing to make sure we did our algebra right? We're going to compare what to what? G and R, right? So we're going to graph G of x. And I want to graph R of x. And let's do blue. And let's turn this one off. So here's what we got by, G is the one we got by algebra. There it is. And we want to see if we did the algebra right. So then we graph the trusted form. They are what we call the difference quotient, right? It's difference, change in y over change in x. When I turn it on, it should land right on top of it. So you saw it turn from, or so let's make this a little lighter. Can you see green on the screen? Yeah, perfect. So green, I'll add red, I should get maroon, right? So this is the way, so in terms of, we're going to be doing lots of derivatives. Lots of derivatives, and you're going to be like, oh, I don't know if it's right. I don't trust my algebra. Use GC. Graph the trusted form and the form that you got using algebra. It should be the same rate of change function. This is a great way to check your answers. Okay? Questions on that? So what you can do is just make a file just like this and save it. And then all you have to do is go in and change the F and the G and the R, and then you just keep reusing it instead of recreating it every time. So just get the generic template for this trusted form, checking your derivative file, save it, and then you can use it. Okay? We're gonna be doing lots of derivatives here, and that's what the mastery test is about. Okay, where am I? There I am. So we checked, and we're good. Okay, next type of function, exponential functions. So what do we got? We got 5 rules now. The 4 that you worked on over the weekend, and then we got the square root of x. Now what about exponential functions? So any base to the power x. We're going to derive the rule. How do we start? Where's Noel? Laura? How do we start? I want to figure out a shortcut rule for the rate of change or the derivative of b to the x. How do I start? Yeah. And what is it? That's it. No, that's not it. That's the answer. Okay, so I guess I'm doing the writing here. Exactly right. So we're going to start with a rate function is f of x plus h minus f of x over h. And then for this particular rule, b to the x, what does that become for this particular rule for b to the x? Where is John, Tanette? John here? He usually sits over there. Not here today. Okay. How about Jayu Chen? Jayu Chen. So now I want to take that rate of change function. I want to apply the rule of b to the x. So what will I get? That's it. We're going to plug the, she said, plug the x plus h in for x. So that's b to the x plus h minus b to the x all over h. Okay, there's kind of only one place we can do anything here. The only place we can do anything here is right here. What is b of x plus h? Right, so that's what? X plus h number of b's multiplied together, right? It's b times b times b times b. How many b's? X plus h of them. So we could rewrite that as x b's multiplied together, and how many more b's multiplied together? H more, right? So this is the same. If you have x plus h total number of b's multiplied together, you could say that's the same as x b's multiplied together, and then h more b's multiplied. And that's the same as x plus h b's. Okay? And now that allows us to do something else. What can we do? We could factor out b to the x. And we're left with b to the h minus 1 over h. Okay? So as h gets essentially 0, as h becomes very, very small, essentially 0, this becomes essentially what? B to essentially 0. It's 1. And so the numerator becomes 0, 1 minus 1. And then the denominator? So this, as h gets really small, this thing here does what? It gets essentially like 0 over 0. Okay, this is called an indeterminate form. And there are 3 possibilities for an indeterminate form. The first possibility so in different situations, 0 over the, quote unquote 0 over 0 has different values. It could be 0. So 3 possibilities for 0 over 0. It just essentially is 0. That could be. Okay, it could get really, really large. Or it could approach some finite value. So let's talk about our context here and see what makes sense. Would it make sense for this thing to be 0? Then what would our rate of change function be? 0. Does it make sense that the rate of change function for b to the x is 0 everywhere? Doesn't make sense. We know we're going to have some legitimate rate of change function. It's not going to be 0 everywhere for b to the x. So we can nix that possibility. What about infinity? So what that would say is that everywhere in b to the x, for every value of x, the rate of change is just infinitely big. Doesn't make sense. No, that just doesn't make sense. Because the whole function would be just getting infinitely large. So that every rate of change at every value of x would be infinitely large. Doesn't make sense. So we're left with that this thing heads to a constant. So as h goes to 0, this thing approaches some constant value. Now that feels better because now this thing is b to the x times k. So notice, so this is like a special situation. When you have b to the x, what is your rate of change function? It's some constant multiple times the original function, b to the x. Okay, that's a very special situation. So exponential functions have this kind of special thing about their rate of change, that the rate of change is a constant multiple times the original accumulation or amount function. And it turns out that this k is, we're not going to show it, but it turns out that this k is equal to, so where k is the natural log of b. So that k is the natural log of the base that you have in your function. So it's a nice simple result for the rate of change of a exponential function. Okay, so I want you to find, so let's summarize that here. So this is what we just found. The rate of change function for b to the x is b to the x, the original function, times k, and that k is ln of b. So I want you to just, real quick practice here. I want you to find the rate of change of 2 to the x and the rate of change of p, 3 to the x. If you're following, that should take you 10 seconds. That should take you 10. What's the derivative of the j function? What's the derivative of p? What's the derivative of j? What's the derivative of p? Okay, what's the derivative of j? Where's Estrelita? Naswood? Estrelita here? Where's Levi? Levi right here. What's the derivative of j? So let's practice some of our new notation here. I could say j prime. That would be one way to say it. And Levi, what is it? 2 to the x times natural log 2. All right, and then derivative of p. Who gets the easiest question of the semester? Vincent Bagnara. Where's Vincent? What's p prime of x, or the derivative of p? 3 to the x natural log of 3. Okay, now I want you to get decimal approximations for those. Get a decimal approximation. We're not going to we're done finding those rate of change functions. But just get a decimal approximation for ln of 2 and a decimal approximation for ln of 3. Go. Get a decimal approximation for ln of 2 and a decimal approximation for ln of 3. We've got a purpose here. What is ln of 2? 0.69. So is the rate of change for 2 to the x at any value of x, is it greater than or less than the original function? If it's 0.69? So the rate of change function for every value of x greater than or less than the original amount function 2 to the x? Less. You're taking up like 70%, 0.69 of it. What about ln of 3? What'd you get for that? Okay, so what about that one? That rate of change function. Greater than or less than the original function 3 to the x?
Greater than.
Greater. So that begs a question. What question does that kind of... If this one, 2 to the x ln of 2, our rate of change is like less than, it's a fraction of the original. And then this, for 3 to the x ln of 3, it's greater than. So that the rate of change function is a multiple of 1 point something, a multiple of the original function. So does anyone see what's going to happen in between 2 and 3? Somewhere between 2 and 3, what's going to happen? Yeah, it's not under overestimating. It's just that the rate of change function is a fraction or less than the original. And here the rate of change function is greater than or a multiple of. So somewhere between 2 and 3, what's going to happen? Yeah, Philip.
It's going to double.
So, well, no, that would be greater than 3, right? Because this was like 1 point something.
Wait a minute, it'll hit 1, so that means it'll be...
Right. So was there a hand over here? Yeah. Yeah.
They will equal the rate of change.
Yeah, so there's going to be for some value of a between 2 and 3, there's going to be the amount function or the rate of change function that ln of that a, ln of a is going to be 1. And your rate of change function is going to be the same as the accumulation function. There's only one function in the whole universe where that's true, where values of accumulation or values of amount are equal to the rate of change for every value of x. There's only one function like that. Okay? And it turns out, so that has to be for some base between 2 and 3, because we saw 2 gives us, ln of 2 gives us a number below 1, ln of 3 gives us a number above 1. So that number is, anybody know? E. That's what E is. E is the special number, 2.718281828459045. Okay? It's the special number between 2 and 3 such that the rate of change of e to the x is e to the x because ln of e is 1. So it would be times ln of e, but ln of e is 1, exactly 1. So really special, really important function. Values of the accumulation are equal to values of the rate of change for every x. There's only one function in the universe like that. Okay? All right, let's look real fast. Let's investigate that. This is just, it's too cool to pass up. Okay, so I'm just going to pick any number here. I'm going to pick, say, boom. Here's, this is our amount function. Our amount function, okay? And I've got the point x equals 2.14062. .045, 8.504. 475 or 8, okay? What's the rate of change at 2.1406? X equals 2.1406. So the amount of accumulation is the amount at that x value is 8.5048. What is the rate of change at 2.1406? What is the rate of change? Where is Ethan Eisner? Is Ethan here? No. How about Ping Yang Yu? Where's Ping Yang? Are you here? Okay, where's William Clark?
It's going to be 2.1406.
So that's the x value at 2.1406. What is the rate of change of e to the x? What is it? So what is the rate of change at that x value? Which is what? Huh? I just wrote it down right here. 8.5048. So let's zoom in and let's show it. Quick, write this down. Let's make sure we're close enough here. What do we need? 2.14. Oh, shoot. There we go. Okay, 2.14. The point is 8.49944. This is all amounts, right? These are all amounts. This is the amount function. 2.14. The amount is 8.49944. And at 2.41, let's do 2.42. At 2.42, 2.142, 8.51645. Okay, so we got local linearity. We've got a really small moment. We've got a really small moment. So I want you to find, this is a 4. Using our local linearity, find the rate of change at 2.1406. Find the rate of change at 2.1406. Go. What's going on? I have. We're back. We're gone. Stay. Okay, did you get 8.505? So look, the y value at 2.1406 was 8.5048. And then we zoomed in at that x value, 2.1406, and we found the rate of change right there. And the rate of change, look, is the same as the y value. That's the big point here. That's the beauty or the specialness of e to the x. This is the amount. This is the rate of change at that same x value. That was the amount, and that's the rate of change, and they're the same. for all x values. The rate of change is the same as the amount. Okay, I beat that. Don't forget it. Important. Okay, so we got another rule. I can't find where I'm at. So that was it. Okay, so here's. I want to press on, so I don't take time to write this down. Like, if you want to get this list, you can pause the video. But we know that for a constant, just a constant, rate of change is 0. Constant multiple times a function, the rate of change is that same constant multiple times the rate of change of the function. The power rule, the rate of change or the derivative of x to the n is n x to the n minus 1. And then we had a sum of functions. If you have a sum of functions, the rate of change is the sum of the rate of change. Okay, so what was square root of x? So now we got square root of x is a new one. We did that today. 1 over 2 radical x. B to the x. B to the x times that constant L and a B. We usually put constants out in front, so I'm going to change the order. Put the L and a B first, but it doesn't matter. It doesn't matter either way. Okay, finally, e to the x. E to the x. Only one function in the universe whose rate of change values are the same as the amount or the accumulation. Okay, so the next thing we need is a practice problem. And then we're going to move on to the next thing. So let's do a quick practice problem. Here we go. Oh, you'll live and die for problems like these in a week. You'll love problems like these in a week. You'll beg for problems like these in a week. They're going to get hard. Okay? So here we go. So what's the overall structure? That's what we're always going to ask in these complicated amount functions. What's the overall structure of the rule? Is it something to a power? Is it a constant multiple times a function? Is it a power rule? Is it x to a power? So what is the overall structure of that thing? Jason, can you tell me what's the overall structure of that? Well, I'll give you two choices. Is it a constant times a whole function, or is it a sum or difference of functions? Yeah, the overall structure is a sum of a bunch of functions. So we're going to apply the sum rule first. So we're going to do the individual, the sum rule says, do the individual rate of change functions for each term. So we're going to start with this, and we come to this one. And we say, what's the overall structure of that? I'll give you another, same thing. Is it a constant times a function, or is it two things, is it added? Yeah, so this is 4 times a function. So the rate of change will be 4 times the rate of change what's inside. And what's inside? What's the structure of that? What's inside the parentheses? Everybody. A sum. And so we're going to do the individual functions. So a to the x, its rate of change is a to the x times ln of 8. Plus structure of that. What rule will we use? Power rule. So it will be negative 8x to the power of. Okay, so it's not negative 7. It's not 1 closer to 0. It's literally 1 less always. So if it's negative, it gets more negative. Okay, it's not closer to 0. It's literally more negative. Okay, plus x, rate of change. It's 1. Minus 2e to the x, which would be minus 2 times the rate of change of e to the x. So I just executed the constant multiple rule and the e to the x rule. So it's minus 2 times the rate of change of e to the x, which is e to the x, plus rate of change of 10.7x. Power rule says 10.7 x to the 9.7 minus 1 over 2 radical x. Or if you want to do 1/2 x to the minus 1/2, it's the same, that's fine. Last one, e squared. Is it an exponential function? Is it a power rule function? Neither. It's a constant. E squared is a number. E squared is a number. It's not an exponential function because there's no x in it. It's not the power rule because it's not x to a power. E squared is a number. Rate of change is 0. We're done. So incorporating, so this is the name of the game. Incorporating the rules in combination. Incorporating the rules in combination. We use the sum rule, we use the constant multiple rule, power rule, square root of x rule, exponential rule, all of it. Okay? Okay, anybody have a question? Okay, so what about rate of change of composite functions? Rate of change of composite functions. Here we go. We saw this before, and we saw this with creating our approximate rate of change function from the exact rate of change function. By doing r of left of x, that created that step function. That was our approximate rate function. So what was the idea? An x value went into left, and that gave us the left side of the current interval. We put that into the exact rate function, and that gave us the approximate rate, or the rate at the left side of that interval, and that was our step function that approximated the original rate function. So this is the idea of a composite function. The dependent variable of one function becomes the independent variable in another function. It's like we're operating functions in succession, right? In succession like this. So that's an example. So now each of these can be seen as composite functions g of f of x. So we'll do this together. So what would be, so f we call like the interior function, and g we call the exterior function. So how could we kind of see this as an interior function plugged into a exterior function? What would the interior function f be? X cubed minus 5. Do you see that that is an interior function? In what exterior function creates m? Square root of x. So do you see that if f was the independent quantity for g, you would get the function m? Okay, what about this one? How can we see this as g of f of x? F would be 3x to the 8, and g would be e to the x. Do you see it? What about this one? Interior function could be 1 over x squared, exterior function. So the question is, what is the rate of change, say of this first one, the rate of change of m, which is a composite function, right? It's x cubed minus 5 plugged into the square root of x. What would the rate of change of that be? So we might have a couple conjectures here. We might think this, right? We're following the square root rule. If we're doing the square root rule, it'll be 1 over 2 times the square root of that thing, x cubed minus 5. So that might be a conjecture. We're conjecturing. Or would it be that use the square root rule and then also take the rate of change of what's inside? So 1 over 2 square root of x, but then instead of x cubed minus 5 would be 3x squared. Okay, or something else, right? So it's like based on the rules that we have, these might be two good guesses. These might be two good guesses for the rate of change of that m function. Okay? And so what I'm going to tell you is it's neither of those. Neither of those are correct. So, and we could show that with GC, right? We could do the trusted form of the rate of change of m, and then we could just graph these two functions. Neither of those functions will match up with using the trusted form for the rate of change of m, right? M of x plus h minus m of x over h. If we graph that, it would not match up with either of these. So we need to figure this out. Okay, here we go. Suppose that a function f has a rate of change r of f, and we know this. And we've been over this many times. This means that if we have a small change in x near 6.1, the value of f will change 3.8 times as much as that small change in x. Right? That's the rate of change. For a small change in x near 6.1, f will change 3.8 times as much as that small change in x. Old hat. We've worked hard on that. So here's that in symbols. The change in f will be that 3.8, or the rate of change of 6.1 times the change in x. Okay? So this is, we're setting up to figure out what is the rate of change of a composite function. All right, so here's a situation. We got two functions, f and g. And we want to know, what we're after is the rate of change of g of f of x. We have some information here. The rate of change of f of x equals 5 at this point. The rate of change of g is 3 at this point. We want to know what is the rate of change of g of f of x. So, if x changes a little bit, how much does f change? If x changes a little bit, say near 6, how much does f change? Let's see if we can do this. Where's Michaela Watkinson? Michaela here? How about David Benrick? Yep. If x changes by a little bit and the rate of change of x is 5, how much does f change? Right, exactly. So the rate of change is going to be the amount that the function f changes. It's going to be 5 times as much. df is 5 times as much as dx. So that's showing that visually. Very good. Okay? And so now, if f changes by this little amount, how much will g change? So now this is our change in f in this function. How much will g change? Where is Brianna Gonzalez? Right. So the rate of change of g with respect to its input is 3, which means if we have this much of a change of f, g is going to change by, oh, we already did that. So g is going to change by 3 times as much as the change in f. So how much does, when x changes a little bit, how much does g of f of x change? Here's our little change in x. How many times that change in x does that function change? Do you see that it's 15? F changed by 5 times the amount that x changed, and then g changed by 3 times the amount that f changed. So the output of g of f of x changes 5 times 3 as much, or the rate of change of f, there's our 5, times the rate of change of g with respect to f, that's our 3, as much as dx. So that is our rate of change, that's m. That's the rate of change of g of f of x with respect to x. So this is the key to understanding the rate of change of a composite function. G is the exterior function, f is the interior function. So first we let x change a little bit, and we're going to have the rate of change of how much f changes with respect to the change in x. And then we have how much g changes with respect to that change in f. Well, that's the 5 times 3. So that forms what we call the chain rule. I want you to practice some of these problems for Thursday, so I want to make sure we're finishing up this up. So the rate of change of g composed with f respect to x is the rate of change of f, the interior function with respect to x, times the rate of change of g with respect to f, Okay? And so the order doesn't matter. We could change that order. So sometimes certain problems we'll think about doing the rate of g with respect to f first, and then r with respect to f. So let's go back to m. We'll do m. We'll be done. So here's m. So what was f? F was x cubed minus 5. Almost done. G was square root of x. So what's the rate of change of f with respect to x? 3x squared. Okay? And then what's the rate of change of g? G is this with respect to f. So what's the rate of change of g with respect to f? Well, it's the square root function, so it's 1 over 2 square root of what? With respect to f. So what's going to go under here? No, not f, not the rate of change of f, f. So this is the rate of change of f. This is the rate of change of g with respect to f, meaning leave f as it is. Leave f as it is. This is the rate of change function.